Good morning, calculus students. We are going to be talking about the integral test and the P-series test. These are two more tests the AP exam is going to talk about. Specifically this year, the P-series test, geometric series test we've already talked about, and we had homework over the break about what that should be. Remember, that's summation where we've got our first term times if we can write it in the r to the nth. And the nth term test for divergence. These are very commonly used, so we're going to take a look at these and jump right into them. So the integral test, in order to use this, there are three things that we need to state first. There's a couple other calculus rules that go like that with like L'Hopital's. We have to be able to do that. The first thing you have to do for the integral test is state that it's positive. There is no alternating terms. They're not going positive, negatives, and there are no negative terms. We need to simply state that all of our terms are going to be greater than 0. It does need to be continuous. We're looking for no gaps or jumps, and it should be decreasing. And we know in calc terms, we know decreasing is f prime of x has to be less than 0. So given a summation from n equals 1 to infinity of a sub n, that's our expression, if a sub n is greater than 0, that's our first one, a sub n is continuous, second one, and it's decreasing, and the integral from 1 to infinity of a sub n is diverging, then the summation diverges. If this converges, the summation is going to converge. And something to keep in mind is if you get a real number for this integral, that does not mean that is the sum of the summation. So the real number that you get from the integral does not equal the summation of the actual expression. If you get this goes to positive or negative infinity, if it's divergent, then the summation diverges. And that's the integral test. So let's take a look at one of those. Here's an example from n equals 1 to infinity of n over n squared plus 1. So what we're going to do is let that function, thinking of it in terms of a function, and it's really an expression, x squared plus 1 for x's greater than or equal to 1, because that's where our summation starts. So we want to show three things are true first. We want to show first that it is positive. So if we are looking at values going to positive infinity, our a sub n is always going to be positive because our denominator is strictly positive. So a sub n is greater than 0. Is it decreasing? Well, let's take a look at two consecutive terms. If we plug in 1, we get 1 over 2. If we plug in 2, we get 2 over 5. So it's decreasing. So a sub n is greater than a sub n plus 1. And this is a continuous function. We have no discontinuity when our x is greater than 1. So we've established those three things first. So now we're going to take a look at the integral. We're going to take a look at the integral from 1 to infinity of n over n squared plus 1. If you want to use x, you can do that. So if we have an improper integral, we're going to change this to be a limit as b goes to infinity from 1 to b of x over x squared plus 1 dx. And now we're going to use our integration techniques. And by some calculus magic, we've got u established to be x squared plus 1. That means du is 2x dx, and therefore 1/2 of du is x dx. So if we're doing that and substituting in, we've got the limit as b goes to infinity of 1/2 of x equals 1 to b of 1 over u du. And remember, you do need to do this if you're not plugging in to your expression for u. So we've got the natural log of the absolute value of u evaluated from 1 to b, which means we're taking a look at the limit as b goes to infinity of 1/2 of the natural log of b squared plus 1 minus the natural log of 2. So if we're looking at this and we're plugging in, quote unquote, plugging in infinity into b squared, we're getting infinity plus 1. And eventually, as we keep getting larger and larger, and we're following the natural log curve, it's going to take a while, but this keeps getting larger and larger because the natural log curve is going up to infinity as x goes out to infinity. So this would be 1/2 of infinity, which is still going to keep going bigger and bigger with every passing second. And then we've got 1/2 of the natural log of 2. So as this gets larger, this gets infinitely smaller and doesn't do as much to our value of infinity as we get, since infinity is not really a number that we can talk about. So if we have our integral that's going to infinity, that means that diverges. Therefore, our summation of n over n squared plus 1 also diverges by the integral test. And remember, in order to use the integral test, you have to establish our first 3 rules. All right, let's take a look at another one. We've got 1 over n squared plus 1. Why don't you pause and give this a shot and see what you come up with. All right, well, let's check your answers. So if we've got our first 3 things established, a sub n is greater than 0, a sub n is continuous, a sub n is decreasing. Those 3 things are all true for this expression. So we're going to switch our summation into an integral, and it is an improper integral, so we're going to go ahead and rewrite that with the limit as b goes to infinity from 1 to b of 1 over x squared plus 1 dx. And this is a great way for AP to see if you know your trig rules. Do you know the antiderivative trig functions? So 1 over x squared plus 1 is arctan of x. So we're taking the limit as b goes to infinity of arctan of x from 1 to b. We're going to go ahead and plug our upper bound and lower bound in and take a look at what the arctan graph looks like. So the arctan looks like this. We have a lower bound of negative pi halves for our range and an upper bound of pi halves for our range because we're thinking about dad. So arctan, as we go out to infinity, is going to get closer and closer to pi halves. And the arctan of 1, of course, is where sine and cosine the same value, and that's at pi fourths. So we've got pi fourths as our answer. That is a real number. So that means that our summation from n equals 1 to infinity of 1 over n squared plus 1 converges by the integral test. Hopefully you got that one right. The next type of test that we're going to look at is called the p-series. So any series that is in this form, where n is our variable and p is a positive constant. P is a positive constant. If I can have it in this form, then this is what's called a p-series. And there's a special p-series called the harmonic series. And the harmonic series is when p is equal to 1. So what we've got is we've got 1 over n to the first. So those terms are 1 plus a half plus a third, plus it keeps going until I have an nth term, so it would be 1 over n, and it keeps on going after that because we have the summation as n equals 1 to infinity. And we're going to be taking a look at this and the p-series test to how to determine if these p-series are either convergent or divergent, and specifically taking a look at the harmonic series. So you can take a look at what we've done with these series right here and kind of start writing them out and take a look at what's going on and look at the integral test for each of these. Here we've got a p is equal to 1. Here we've got a p is equal to 2. Here we've got a p is equal to 3. Here we've got p equal to 1/2. Here p is equal to 3/2. And here p is equal to 4. So take a moment and look at the integral test for these and try to determine what you think the p-series test is. So we're going to take a look at the p-series, and this one is called the eyeball test. This is going to be assessed this year, and which is awesome because it's an eyeball test. You kind of look at it and you kind of see right away if it is or if it's not. So if you took a look at the integral test for the ones listed previously, any of those values where p is greater than 1, you'll notice that those series converge. And the summations where p was between 0 and 1, those are going to diverge. The harmonic series, which is that special one where p equals 1, so we're looking at that summation of 1 over n from n equals 1 to infinity, and you'd think that this would get too small eventually as n goes to infinity, that it were basically adding 0 each time, but with this one, it's enough where it's going to make this diverge. And you have to be super careful because in these two tests in particular, comparing the p-series and the geometric, for the geometric, when we've got our r value that we're looking at, as long as the absolute value of r is greater than or equal to 1, then it diverges. And if the absolute value of r is less than 1, then it converges. So it's a little bit different than what we've got here. So you have to be really, really careful with these two series. But let's take a look at a couple. And we'll take a look at one of the special cases that comes up. And this is a special case because this is alternating. So this is called the alternating harmonic series. And I'm not going to spoil this one for you because we're going to be taking a look at it when we look at all alternating series in a little bit.